So looking at this table here of the summary of solar geoengineering options from this Royal Society paper, we are looking again at stratospheric sulfates and other stratospheric aerosols like aluminum and I think titanium oxides, if I remember correctly. Marine cloud brightening, cirrus thinning, and space-based mirrors, and so on. Confidence that substantial global radiative forcing greater than 3 watts per meter squared is achievable. So right now the additional radiative forcing because of the accumulated greenhouse gases since industrial revolution is I think around 2 watts per meter squared. So we are planning to increase the loss of incoming shortwave more than 3 watts per meter squared, then we would definitely start compensating for the warming. It is not a counter solution of global warming. It is additional climate change on top, as we will see. Okay, so sulfates, there is very high confidence. With other stratospheric aerosols, it's moderate. Why do we want to consider other aerosols? Because of the potential impact of sulfates on the ozone hole and so on. Marine cloud brightening is quite uncertain, and cirrus thinning is uncertain, and space-based mirrors is low physical uncertainty but also deep technological uncertainties. Advantages: similarity to volcanic sulfate gives us empirical basis for estimating the efficacy and the risks associated with spraying sulfates into the stratosphere. Other stratospheric aerosols spraying, some solid aerosols may have less stratospheric heating and minimal ozone loss. So the sulfate aerosols also may become bigger drops and reflect less efficiently the short wave and end up heating the stratosphere, increasing humidity, and create other issues that I will discuss in a minute. Marine cloud brightening, ability to make local alterations of albedo and modulate on short time scales is an advantage. Works on long wave radiation, so could provide better compensation when we consider cirrus thinning. So this is less damaging in other ways but has these advantages. The space-based technologies, possibility of near perfect alteration to solar constant is offered by this approach, and there are disadvantages: harder to bound uncertainty since these are not naturally occurring, so we don't have much empirical knowledge. The marine cloud brightening is only applicable on marine stratus covering approximately 10% of the Earth, means radiative forcing is inherently very patchy. So you have compensating circulations happening then, and you don't know what will happen. Maximum potential cooling is limited in cirrus thinning. Zonal distribution of radiative forcing is constrained by distribution of cirrus, which are naturally occurring clouds. And space-based technologies are substantially more expensive, considering they have to be at order 400 kilometer in altitude. This study also looks at the way that solar engineering would contribute to modifying business as usual, which is what we are on, as we said in the beginning, to justify the inevitability of geoengineering. We said despite 25 years of negotiations, we are on this trajectory. So carbon dioxide removal, or CDR, is probably going to bring us down in terms of cutting emissions, and then solar geoengineering can give us quite a substantial reduction in climate impacts. You can also make it more specific in terms of temperature targets, so this is business as usual. Mitigation, Paris Agreement, and commitments to nationally determined contributions, policies, renewables, etc. will probably bring us here, including mitigations, other mitigations. Carbon dioxide removal will further lower the temperature target by longer time horizon. So we are here in 2100, and solar radiation management, in addition, can keep us below 1.5 degrees according to this calculations. And the calculations also show the change in temperature between 2091 and 2010, when there is no geoengineering, and the associated precipitation changes. Remember, the volcanic eruptions created lots of droughts and reduced rainfall. But with geoengineering, you are reducing the temperature warming from 2.7 to 1.5 with dynamic patterns that are not easily predictable. So you can see there are regions that warm more and there are regions that warm less, so the Arctic amplification still remains. With geoengineering, the rainfall reduction has gone from 5.1% in the greenhouse world to 2%. This is something that is argued in a couple of papers. So if this is true, that could be important. We will discuss this in a little bit more detail. And if you look at longer horizons from 2019 to 2038, in the shorter time horizon, to keep temperature change to 1.5 degrees C or less with no geoengineering, this is the warming you would end up with. This is the precipitation change you would end up with. But it's pretty clear by now that the trajectory we are on in terms of emissions, we are going to blow past this target very quickly. But it's fair to say that this target is not really greatly scientific. It started with the somewhat political target of 2 degrees centigrade, and then a special report was produced by the UNFCCC in 2018 to look at 1.5 degrees centigrade target, and arguments were made that this would be much safer, and the additional half a degree warming from 1.5 to 2 degrees C would do much more harm in the physical, biological, and human managed systems, and the increased risks in all of them, and so on. So this remains something that is discussed heavily, just like geoengineering is a huge social, political, socio-economic problem. Greenhouse world itself is going to be the same as well. The scenarios that are being considered, that we talked about in terms of renewables and mitigation and adaptation, are not guaranteed to work, and there is inevitability of carbon dioxide removal, but we are talking here about additional geoengineering approaches, of course. So in the next podcast, we will step by step discuss the various technological barriers and other impacts we have to consider should we choose to do solar dimming or noontime reduction in solar radiation to the surface.